Okay, so good morning, everybody. Today we are going to comment the paper called Adaptive Object Detection Using Adjacency and Zoom Prediction by John-Chi Liu, Tara Javidi, and Svetlana Lazebnik. And Miriam Bebe will present this paper, which will be actually presented publicly in CPR 2016 next week. So Miriam, the floor is yours.
Well, I'm Miriam, and I'm going to talk about this paper about adaptive object detection. And well, here you have the links for the archive and the code that is publicly available. First, I'm going to make a brief introduction. Okay, well, as you all may know, the typical pipeline for object detection consists on a set of region proposals, and then a detector that labels and scores these region proposals in order to have the detection. Why do we use region proposals? Because like this, we are only focusing attention on certain parts of the image, and it's more efficient. Okay, nowadays, the generation of region proposals can be really efficient because of the sharing of convolutional features. And in fact, there's an emerging class of region proposals that are learned end-to-end using deep learning. And well, they are based on something that is called predefined anchors. What does this mean? For instance, if we have an image and we have, we can divide it into a grid, as YOLO does, and each of these boxes of the grid, we can use them to predict a bounding box, to regress these boxes and obtain a bounding box. And this is this new class that uses these predefined anchors in order to predict bounding boxes as object proposals. Then this paper is different from other approaches like faster RCNN or YOLO, because instead of having a fixed set of anchors like a grid or a sliding window fashion or whatever, it uses adaptative anchors. It adapts to the content of the image, and depending on it, it has a set of predefined anchors in order to predict the bounding boxes. And well, as the other approaches, from these anchors, extracting the features of these anchors, it decides if it's required to use more anchors, and from them, it extracts the object proposals. Okay, here we will understand a little bit better all this. If, for instance, we have this image, and we predefine 5 anchors that are the 4 corners and the central region. We can analyze these 5 initial anchors, and from each one, we decide if we want more anchors. For instance, for these first 2 regions, no more anchors are needed because there's no object inside of interest. There's not a small object that requires a more deeper anchor. There's another region, the third one, that after extracting features, the algorithm decides, okay, we need more anchors from this region because there's still some small objects like some car. So we divide it again with these 5 anchor regions. And then you have again these 5 regions. So this is the methodology of this paper. It has first an indicator that says if you have to further divide each region, and from each anchor, it predicts some bounding boxes. Okay, then the contributions of this paper are these: to use adaptative anchors in order to obtain object proposals. And in fact, they achieve similar, they use the PASCAL VOC and Microsoft Coco database, and they achieve similar performance compared to fast and faster RCNN, but using fewer anchors. And well, in fact, 2 orders of magnitude fewer anchors on average than fast and faster RCNN. Okay, in the paper, they first comment some previous work. Well, some months ago, I presented this paper of the same authors about adaptative active object localization with deep reinforcement learning. And in this paper, what they did, it was initially they saw the whole image, and from it, they trained an agent using deep reinforcement learning that decided how to deform an initial bounding box until fitting an object. For instance, you have here the whole image, and they said, okay, let's make it smaller, let's move to the right, to left, etc., until I found the object. Like this, they achieved with a few steps to find objects. So that's the whole proposal, to to analyze a few regions. But the problems of this paper, and for this reason they tried a different approach, were that they needed to train as many networks as class categories they wanted to detect, which was not very efficient. And although it was really fast during test time, I did not achieve state-of-the-art accuracy. Then they focused on this use of anchors in order to obtain region proposals. Well, I have already commented that YOLO uses this, multi-box, faster RCNN, and the difference is that they adopt an adaptative approach. Mainly, they compare to faster RCNN. So I want to explain a little bit. Well, it's more or less, they have a picture and they also obtain some anchors, but this time they are obtained from a sliding window fashion. And from these anchors, they do the same. They regress until obtaining a tight bounding box around the object. In this paper, what they say is that they are better at localizing the approach of adaptative anchors. It's better at localizing, for instance, the small objects that sometimes faster RCNN misses. Okay, about the design of the algorithm. Okay, then first we have a network that they call AC network. And from this network, they obtain this set of object proposals. And then they introduce these object proposals to an object detector. And in this case, they use the fast RCNN detector in order to compare to them. So, well, in this case, they only focus on the first part in obtaining efficient object proposals. Then, how does this network work? Okay, here there's a diagram from an anchor that we have said that from an image, we divide it into first 5 anchors. For each anchor, they have a network that predicts a zoom indicator. This zoom indicator says, okay, you have to further divide this region or not. If it's active, you divide it. So if it's above the threshold, you divide it again. There's another branch that from that anchor, it obtains some adjacency predictions that would be like bounding boxes or object proposals with a score. And if that score is above a threshold, that's the object proposals that we are storing. And this is like a recursive pipeline. Let's first talk about the zoom indicator. Okay, the reasoning of the zoom indicator is that the prediction of the indicator should be high when zooming achieves a better chance of detection. For instance, here we have 3 cases. The green boxes would be the objects, and the red ones, the anchors. In the first case, if we zoom, we lose the object. So in this case, we are not interested in zooming. In the second case, if we zoom, we lose area of the object we are trying to detect. So in this case, we would not zoom. And in the third one, we have a small object inside the anchor. And in this case, we would improve accuracy if we just zoom into it. So in this case, we are interested in an active zoom indicator. Okay, about the adjacency predictions. Okay, in order to train this network from a set of anchors to define, to regress them in order to have some tight bounding boxes around the objects, what they do is they work with some subregion priors from each anchor. So imagine that we have one anchor that is the red box, and from it we define 10 different regions around them. For instance, here it would be bounding boxes that are vertical, horizontal, or around it. This could be possible bounding boxes regressed from these first anchors. So they use them in order to train. Okay, then the implementation. Okay, here we have more or less the architecture they use. From an anchor, that would be, for instance, an anchor. We obtain a convolutional feature map that they obtain from BGG 16. And each of these prior subregion priors that I have explained here, they project them into this feature map in order to be efficient and to share features. And they also introduce the whole anchor. And well, they have a Roy polling layer that it's a layer that it's used in faster CNN, I think, in order that it's good at propagating deparameterized bounding box, something like this. And then, well, we have three different outputs. One is the zoom indicator that indicates if we should further zoom. And then the adjacency prediction, the bounding boxes, the parameterized bounding boxes, and a score for each of these bounding boxes. And these are the three outputs. Okay, so in order to implement this, first we need to sample from the image to obtain positive and negative samples. In fact, we are interested in hard positive and hard negative, and then train it using these samples that we obtain with stochastic gradient descent. Okay, in order to have hard positive, because if you first have an image and you divide it with the predefined regions, maybe you don't have a sample that it's covering the full ground truth. And in order to train, we are interested in having hard positives. And for this reason, what they do is when they have a training image, they focus on an object, and in that object around it, they add all these, they add the anchor and all these subregion priors in order to have some hard positive samples. And they do exactly the same, but for the negative. So in order to train, they adapt a little bit their anchors in order to have hard positive and hard negative. Okay, another thing that it's important is because it's two things that they are trying to learn, this zoom prediction and then the adjacency predictions. It could be possible that if we use the predictions during learning of the zoom, we can affect the prediction of the adjacency predictions learning, because if we are not during learning, if the zoom prediction is incorrect, maybe it could lead to bad training of the other parts of the network. So for this reason, they decide to don't use the zoom predictions during learning and use class labels. They directly use the labels of zoom prediction for training the adjacency predictions. And well, they saw that this could lead to overfitting, because of course during test you don't have these labels. So they decided to add some noise to the zoom labels. And also in order to train, they use some data augmentation. Okay, finally, in order to train, we have seen that there are three outputs, the zoom indicator, the bounding boxes, and the score related to the bounding boxes. So we have three different losses for each output. For the zoom indicator, typical binary cross entropy. For the bounding boxes, L1 loss error function. And then for the scores, element-wise cross entropy for score output. And what they do is they aggregate these three losses and they do a multitask loss function. And well, as explained in the beginning, after that we have an object detector that we said that it is a faster CNN detector, so they don't do nothing in this sense. Finally, some results. Here there are some qualitative results in order to understand what it is doing. For instance, here we have a picture, and from it we have the anchors that the algorithm decides to work with. These are the initial anchors, and from one of these anchors, they do a regression in order to obtain a tighter bounding box. And these are like the bounding boxes they obtain. And here the same. We see that the anchors are around the objects, but they are not tight enough. But when we regress, then they are better. Okay. They first test all this in Pascal. Well, I don't know if you can see this table. I have made a zoom for the first classes. And well, they achieve similar performance compared to fast and faster CNN. In fact, for some classes, they achieve better, in others not. It's more or less the same performance. But what they state is that they use fewer anchors in order to achieve it. So that's their goal. Also, the quality of region proposals. They have compared, for instance, if they threshold, they obtain a set of region proposals. If they threshold them at certain intersection over union and see the recall with that set of proposals, they can observe which proposals are more accurate. And we see that the proposals of the AC network are better than the faster CNN in all cases. And here, for instance, there's a graph that indicates the number of matching proposals. Matching, they consider that it matches more than 50% with the ground truth. And they compare with the small, medium, and large size proposals with the faster CNN and AZNet. And AZNet works better in all cases, and especially in the small objects, that it's their intention in zooming. And well, this is a similar graph than the other that compares with the number of region proposals, which is the recall achieved, and it's always better with this approach. And finally, here it's during test time, how many anchors are evaluated in order to obtain the objects. We see that it's a tail distribution, so the median is 40 anchors, but in fact, almost all images with a dozen of anchors is enough. And then they have also done some tests on Microsoft Coco. And well, here the metric is average precision, and they obtain similar results compared to faster CNN. But when faster CNN uses this different pre-trained network, the ResNet, instead of VGG16, these results are much better, but it's normal. And well, finally, some conclusions is simply that it achieves the same accuracy, but it analyzes fewer regions. So it may be changing they say that changing the pre-trained model to ResNet would even improve the results. And that's all.
Thank you very much, Miriam.